I hope all of you got this study pack printed, study pack 9, which is chemical periodicity. In this study pack, we'll be studying about the chemistry of the period 3 elements. Periodicity meaning how the properties of the elements varies across the period, such as chemical properties and physical properties. This is the first the chapter on the inorganic chemistry, right? So we just completed physical chemistry in the previous lesson with the kinetics. So from today onwards, the inorganic chemistry lessons will start, and then we'll end up with the organic chemistry. So starting about the chemistry of the period 3 elements, how they are boiling points, melting points, changes, what is atomic radius, and how various different elements of the period 3 reacts with oxygen, halogens, and how their oxides behave, the amphoteric nature, the acid-base nature. All those details will be studied under this chapter. To begin with, let's see what is atomic radius and how this atomic radius is measured. Now, the atomic radius is defined as the distance between the nucleus and the outermost electron. It's not the outermost shell. I notice often many students, they define atomic radius as a distance between the nucleus and the outermost shell, and that definition is wrong, because any atoms has shells till infinity, right? Any atoms have shells till infinity. Because the nuclear charge is limited, the atoms cannot hold electrons till infinity. So it will hold electrons only up to a certain level, right? So the atomic radius is the distance between the nucleus and the outermost electron. But the problem is, it is not easy to say precisely where the outermost electron is held, right? Because to say that exactly the idea of atom has fixed sizes is not accurate, not correct, because atoms, the electrons are not in specific point. It starts rotating, so they don't have exact perfect radii, right? So even electron density map, if you take the electron density map of an atom or a molecule, you will see each time a slight variation of the radius, right? Electron density map will show how the electrons of the atom move, the movement of the electrons, how the electrons, which area of the atom the electrons are concentrated. That shows, it is shown by electron density map. It's multiple times, thousands of times, multiplied the size. You can notice, for example, if you take ionic substance, we have discussed this before. This will be the electron density map of, say, sodium chloride, right? So at one point this will be, but again later on you will see slight changes. But if you take a covalent molecule, there will be a common electron density in between, right? It will be like this. For example, hydrogen chloride molecule, right? So likewise, electron density map gives us understanding of where exactly the atom begins and where exactly it ends, right? So the thing is, now how can you measure the atomic radius? Now, the atomic radius can be measured when atoms, they form bond with another atom, right? So, for example, if you have a covalent molecule, you take, say this is a nucleus of one atom. It forms a covalent bond. It's the nuclei, and it forms a covalent bond with another atom, right? You take the internuclear distance and you divide that by 2. This is what is known as a covalent radii. That is the atomic radii when a covalent bond is formed between two atoms. You take the internuclear distance and you divide it by 2, right, to get the covalent radii. You notice the covalent radii is not the perfect atomic radius. You can see when an atom forms a bond, a covalent bond, what happens, the nuclei will come closer towards the electrons, and as a result it becomes little like smaller, slightly smaller in size than the correct atom, right? So the covalent radii is the closest to the atomic radius. In fact, that is also not the true atomic radius because we can't measure the true atomic radii, right? And then likewise, the metallic radii can be measured. Metallic radius is a radius between the two cations in a metal, right? If you take a metal, you take the two cations, and this is a metallic bond. You take the two cations and you divide the distance by 2. You get the metallic radii. Right? So that's also is not accurate, but that's the only way to form or to find the atomic radius of a metal. Right? So atomic radii is a distance between the nucleus and the outermost electron. The point is that it's impossible to say precisely where the atom begins and ends. The idea that an atom has a fixed size is not correct according to the electron density diagrams, because each time for a molecule or atom you get slightly different electron density map, because electrons are not in a fixed position, they keep moving, right? So how the electron density map is produced? The high energy X-rays knock those electrons and get deflected to a huge screen, right? So many times multiplied. So that's how you see the atom. Therefore, the size of an atom can be estimated by measuring the distance between the nuclei of atoms when they form or when they bonded together in a metal or in a covalent molecule. By dividing the distance by 2, the size of an atom can be estimated. Therefore, measurements on metals provide us metallic radii, and covalent molecules the covalent radii. Please copy this. So you can label them. This is covalent radii, and this is metallic radii. Both of these radii actually they are slightly smaller than the actual atomic radius, because as I mentioned, the shared electron pair, because of the shared electron pair, the nuclei comes closer to the close to each other, and also the electron density map, if you analyze the metallic bond, even due to the free delocalized mobile electrons, the cations come closer. So it's not the true atomic radius. So atomic radius of covalent molecules can be measured by covalent radii, and you have the metals, the metallic radii. Okay, the next question is van der Waals radii. The question, how the noble gases, you determine the radii of the noble gases, because noble gases don't form any bonds, right? Because they are inert, inactive. Of course, there are noble gas compounds made like xenon hexafluoride, for example, that is by giving a lot of energy and forcing the molecule. But generally, noble gases don't form any bonds. So in that case, we can use van der Waals radius. Now, van der Waals radius is radii between the two molecules or monoatomic element. This is, for example, say two hydrogen atoms. You take the distance, internuclear distance between these two atoms, these two molecules, and you divide it by 2. So this is one molecule. You have another molecule. You take this internuclear distance and you divide that by 2. V divided by 2. V is the van der Waals radius. So van der Waals radius is the radius between two molecules, right? So it's much, much greater than the any other type of atomic radius, whether it's covalent or metallic. So the same thing can be done with noble gases. You have two helium, two neon. They don't bond, right? So all what you can find is the van der Waals radius. Van der Waals radius, right? So that's why when you determine the atomic radius of atoms across the period, we'll discuss that in the next question. It decreases, and we'll discuss why it's decreasing. And then eventually, halogen will be so huge. I mean, the noble gas will be so huge. Reason? Because for noble gases, van der Waals radius. Van der Waals is intermolecular attraction. So when the molecule forms intermolecular attraction, the distance between the two molecules or two monoatomic elements, because once intermolecular attraction is formed, the molecule won't so much, it won't freely move. It will be slightly restricted. Their movement will be slightly restricted, right? So then you can form or measure the distance between the two molecules, as referred to as the van der Waals radii. Please copy this. Let's see how this atomic radius varies across the period. When you say across the period, what I mean by across the period is from left to right. Whenever I say across the period, throughout this lesson, what I mean by across the period is from left to right, not from right to left. Now, what happens across the period from left to right? The number of shells are constant, right? Number of shells won't change. Of course, down any group, the number of shells increases. So as a result, atomic radius increase down the group. That's different. But across the period, number of shells are constant. But what happens? The atomic radius decrease, even though the number of shells are constant. Right? Reason is that the nuclear charge is increasing across the period. For example, sodium is plus 11, magnesium is plus 12, aluminium is plus 13, silicon plus 14, phosphorus 15. So the nuclear charge is increasing. When the nuclear charge increases as the number of shells are constant, what happens is that electrons will be drawn more and more closer towards the nucleus. Electrons will be drawn more and more closer towards the nucleus. As a result, the atomic radius decreases. So the number of shells are constant. That means the shielding effect is the same. We say constant shielding effect. Even though the number of shells are constant, yet the atomic radius decrease across the period because the nuclear attraction increases, meaning effective nuclear attraction increases across the period. So as a result, these electrons, the shells will be hurled more and more closer towards the nucleus, right? So across any period, the atomic radius decreases for that reason. So let's plot a graph to show the variation of covalent radii against atomic number of period 3 elements, right? So for the covalent radii, when you see across the period from sodium to argon, sorry, sodium to, yeah, argon, that's right. Neon is period 2, this is period 3, right? Yes. So you can notice like this: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Look at this: argon. What has happened here? In fact, the argon should be the smallest, right? Argon should be the smallest, but here the argon has become the largest. What's the reason? Why argon has become largest here? I mentioned across the period, the atomic radius decrease. So argon has plus 18 nuclear charge. Sodium plus 11. Argon has plus 18. It should be the smallest. So why it is the largest here? Yeah. That's right. For argon, the van der Waals radius is plotted. The van der Waals radius is the biggest, right, than any other atomic radii. Please copy this. Right, so the next, let's see how the ionic radius varies across the period. Now you take across the period 3, because our study is mainly period 3 chemistry. So you have, when it comes to ions, you get these ions. You have sodium forming sodium ion, unipositive, magnesium dipositive, aluminium tripositive, silicon tetrapositive, phosphide trinegative, sulfide trinegative, chloride uninegative. So unipositive, dipositive, tripositive, tetrapositive, trinegative, dinegative, uninegative, right? As for argon, there's no ionic radius because argon doesn't form any ions. So when it comes to cations, now see anions in your naming, phosphide. Now this sodium, you don't say sodition or magnetion. No, ide is added only for the anion, negative. Phosphide, sulfide, chloride, this is sodium, magnesium, aluminium, silicon, right? So now when the silicon 4 plus, if you take silicon 4 plus for example, silicon 4 plus is formed when you remove 4 electrons from silicon. Aluminium 3 plus 3 electrons, magnesium 2 plus 2 electrons. Likewise, when you start removing more and more and more electrons, what happens? The rest of the electrons will be drawn much more closer towards the nucleus. In other words, when you keep ionizing, removing electrons, the rest of the electrons will be drawn much closer towards the nucleus, held strongly towards the nucleus. Right? It will be held strongly towards the nucleus. Right? So as a result, the atom becomes smaller in size. So silicon 4 plus is the smallest out of